I'm in favor of starting. Okay, let's see, maybe a recap. Let's recap where we are in the semester. Today, 26th, is due date for exam 2 on chapters 4, 5, and 6. And we're going to start a new topic, chapter 7. In fact, we're only going to go through about half of chapter 7. That gives us plenty of time to cover the subjects thoroughly. And there's a pretty good break spot between 7.8 and 7.9. And these, by the way, are sections in the textbook. So they correlate to the chapter structures. Let's see, labs. Lab 6 is due detecting signs of chemical change. And then we'll start Boyle's Law today. And we're going to cover that topic in today's lecture. All right. That's enough for recap. Let's start with the materials. So I'll share the PowerPoints. Oh, before I get started, any comments or questions before I move on?
No, there's no questions.
Okay. We'll start with chapter 7, and I'll share the PowerPoints. Here we go. Come on there. Okay, and I need to, let's see, where's my slideshow button? There it is. All right, let me rearrange something here. There we go, so I can see the whole screen. These PowerPoints are as much for me as they are for you. Keep me on track. All right, we're going to, chapter 7 is covering the physical states of matter, gases, liquids, and solids. And we're particularly going to look at the historical progression of understanding of gases, liquids, and solids. And that tends to start with gases, and for good reason, which I hope to explain as we go along. So we're going to go down through 7.8, right? And then there'll be a break, and next Monday we'll pick it up with 7.9 and finish the chapter. Okay. Physical properties. There's a difference between physical and chemical properties of matter, and they're important distinctions because if we're studying chemistry, we need to be able to differentiate between what is a physical change and what is a chemical change, because you don't want to waste time and effort on, or you need to understand physical changes so that your chemistry is better understood and explained. You need to separate the physical changes and properties from the chemical properties and changes. We characterize matter in terms of volume, which would be its shape. Does the matter hold its own shape, or does it require a vessel? Then once we've defined in terms of volume, we also need to include how much matter is there. And typically we describe that in terms of mass, because mass will not change no matter where it is in the universe. Now, of course, we can also describe how much there is in terms of numbers. And that's where we get to the subject of counting. And we've covered that in previous chapters. But when we describe a physical property of matter, we also need to differentiate between whether it's an extensive property, which I like to call capacity, or is it an intensive property? The difference being, if it's an extensive property, then the description depends upon how much matter there is. Volume would be one of those. If you have more of it, it takes up more room. If you have more of it, it weighs more, it has greater mass. But if we take both of those physical properties and combine them in a ratio, call it density, then we have mass per unit volume. And now we have an intensive property. And intensive properties do not change with amounts of the substance. We could have a room full of gold, and it would still have a density the same as a coin. Okay, so we'll come back to that one and probably use density again in calculations. Compressibility. We can describe gases, liquids, and solids in terms of their compressibility. And in fact, solids are incompressible. That is, you can put them under as much pressure as you want, and for all intents and purposes, except under extreme environments like the center of a star or a black hole, solids are not compressible. Liquids, we can consider them under a wide range of conditions as being also incompressible. That's why hydraulic fluids are so useful, because when you push on a hydraulic fluid from one end, say press on your brake pedal, and it forces a piston down against the brake fluid, that force is transmitted instantly to the other end of the line at the calipers on your disc brakes. And that's because it's incompressible. There's no squish in it. In fact, if you're a mechanic, an auto mechanic, you understand that if there's squish in the brake, you've got air in the lines, and you better bleed them again. And that brings us to gases. Gases are compressible. In fact, our understanding of gases depends upon compressibility. Now, of course, under extreme conditions, some liquids are compressible. Density measurements have been made of water at the surface, ocean surface, and at depths of 2, 3, 4, however depth, say 2 miles down, 10,000 feet or 12,000 feet. And the density measurements of water at those depths increases. In other words, you get more water packed into a smaller volume under that pressure. Very slight difference, but it's measurable. But for all intents and purposes, liquids and solids are incompressible. We may describe matter in terms of thermal expansion. Right? We know that if you heat something up, molecules get faster, they bounce against each other. That means they want more room, and they get some of it. If it's a solid, they only get a little bit. So if you heat up a solid, generally speaking, it expands. And in fact, there are quantitative measurements of solids. One of them is called the coefficient of linear expansion. And it's very important to understand what that value is. If it's a very small value, then with each degree Celsius increase, the solid will not expand linearly very much. Okay, I've got another one. Okay, there we go. For instance, railroad segments will, in early days of building the railroad system, there was quite a bit of an expansion in the steel that was that formed the rails. So they had to put gaps in them. So from one rail to the next, there's a gap, and then they put brackets on either side, which were would hold them in place, except it would let them expand. And that's why when you ride across old rails, you hear the clickety-clackety of the wheels. They're hitting those joints. Nowadays, they can build rails on railroad lines of a mile long or more with no expansion joints, because the coefficient of expansion is very small. The alloy of steel that's used is specifically designed to have a very low coefficient of expansion. Now, there are other measurements of expansion. You can have coefficient of volume expansion, which would be useful for gases and some liquids. Liquids tend to expand more with an increase in temperature, and gases a lot more. So if you're preparing a solution, say, in the laboratory, and you need to have a specific volume as your target for that solution. Pardon me. Then when you're trying to dilute to a specific mark on your volumetric glassware, to be sure that you have that final volume, it needs to be pretty close to room temperature, because most volumetric glassware is calibrated for room temperature. 25 degrees is the standard. So if the solution you're preparing is endothermic in the process of dissolving, then that means the liquid is going to be shrinking with that temperature. And if you fill it up to the mark at that temperature, then when it comes to room temperature, it's going to go past the mark and your volume is in error. All right, so thermal expansion is one physical property that needs to be kept in mind when you're doing chemistry in the lab. All right, those are just examples of physical properties. We can think of a number of others. There's no mention of temperature, right? Well, temperature is, technically speaking, a measurement, not a property. If you speak of temperature in terms of specific collection of matter, you may say something like, if we increase the temperature of this chunk of, let's say, water, let's just say you have some water. Say you have 1 gram of water. And if you increase the temperature of that 1 gram of water by 1 degree Celsius, then the amount of heat required is about 4.18 joules. So that's specific for water. It will be different for something else, like iron would be a different value. In fact, it's about 1/10 of that. That's specific heat capacity that I just described, and it's an intensive property. It's characteristic of the substance, and it doesn't matter how much you have. Okay, so there are a number of different physical properties of matter that can be described and are useful in varying situations. These slides are specific visual aids for what I've already described. So I'm not going to rehash this one. We've already talked about compressibility, what it is. And compressibility is an intensive property. In other words, it doesn't matter how much you have of the matter. Compressibility will describe it, whether it's a gram or whether it's a million grams. Thermal expansion, right? That's an intensive property for matter. Now, we need to define characteristics of the states. Right? Solids have a definite volume and a definite shape. And we sort of intuitively understand that a solid, like this marker, holds its own shape, and it has a definite volume. Okay? And the volume only changes if we change, say, the temperature. Liquids have a definite volume, but they don't have a definite shape. So a liquid would need a container, like this cup. Now there are solids in here also, but the liquid in the container needs that to hold its shape. Gases, on the other hand, don't have a definite shape and don't have a definite volume, which means they need a container, and they don't just need an open container like a cup. They need a sealed container. If you want to define the volume of a gas, the container must be sealed. If you open it to the outside, if it's not sealed, then either gas will rush in or gas will rush out, depending on the pressure difference between the two. But the size of the vessel defines the volume of the gas. Okay, those are distinctions of the different states. In general, solids have a high density. Now, why would that be? Well, you're packing a lot of atoms and molecules into a small space, right? And if you look at the definition, I shouldn't have erased it, but I can write it again. If you look at the definition of density, mass per unit volume, if you pack more mass into the same volume, say we're comparing a gas, liquid, solid, and we got a definite volume, say 1 liter. If you fill up that liter with a solid, you're going to have more mass in it because the molecules, the atoms are closer together. There's less empty space. For a liquid, there's some expansion. Most liquids are less dense than solids. But gases, there's very small mass, very few particles by comparison in that same volume, which means the density is much lower. And it all requires that relationship. Right? If we were to take the same mass and decrease the volume, say in a gas, you have a mass of gas in a different volume, you decrease the volume, you got the same mass, smaller volume. Remember, if the denominator gets smaller, the quotient gets bigger, so the density would increase. Compressibility. Okay, we mentioned that before. Solids and liquids are generally incompressible. Gases have large compressibility factors. Thermal expansion. Solids are generally very small, change in volume with a change in temperature. Liquids also, but a little more so than solids. Now, what's the difference between a solid and a liquid that allows these properties to be described the way they are? Solids tend to be locked into sometimes a crystal lattice, and sometimes they're amorphous, but they're still not much room to move. Right? So that's why a solid holds its own shape. Liquids, on the other hand, are free to move past one another. They still interact. There's still intermolecular forces holding them together, but they're not strong enough to keep them from slipping past one another. So liquids need the shape of a vessel to hold them because they tend to move past one another. And there's a little bit more room. There's more space between them. Gases, on the other hand, there's huge space between the molecules in a gas. They behave as if there's nobody else in the room, right? We know that's not true, of course. They bounce into each other. We're going to talk about that in just a minute. But the amount of empty space gives the gas a large volume. And it makes the vessel necessary to define the volume of a gas. They have fairly large thermal expansion coefficients, and that was one of the early laws that was developed concerning gases that we'll talk about in a minute. It's called Charles' Law, that relates the volume to the temperature. All right. So, explaining these properties, I've introduced the topic, but I didn't give it a name, right? Talking about how those molecules interact. There is a theory that addresses this topic. It's called the kinetic molecular theory of matter. In fact, the kinetic molecular theory was first proposed for gases, and then it was expanded to include liquids and solids. But its earliest understanding was in terms of gases. First of all, you have the premises, right? If you're going to propose a theory, you've got to have established ground rules. So first of all, you have to assume that matter is composed of very tiny particles, atoms, molecules, ions, whatever the case may be. And that these particles, each particle has its definite mass and shape and size that does not change. Right? So if you have a molecule of oxygen, O2, right, two connected together, it's diatomic, then that's it, and it doesn't change, right? And when you push on it, nothing happens, right? It might repel you, but you don't get a change in volume. And you have, second, we sort of left out something in here. Matter is composed of tiny particles, and there are a lot of them. Even for gases, in a given volume, say a liter, there's a huge amount. Well, 22.4 liters of a gas will be 1 mole, 6.022 times 10 to the 23rd molecules in 22.4 liters. So that's a large volume, but it also has lots of molecules in it. So you need a lot of them. Now, we have to assume that these particles are in constant motion. Of course, if they're anything above absolute zero, there's going to be some motion. Right? Absolute zero is a theoretical basement that establishes no motion at all. So anything above absolute zero, there's going to be motion. And the higher the temperature, the more motion. But we have to assume that this motion is random. And the reason that we have to assume it's random is that we don't have the computing power or the detection technology to track every molecule in a given mass. If we could do that, then theoretically we could say where everything is at any given second or picosecond and describe it in those terms, but we don't. So what we do is we describe these characteristics statistically. What's the highest probability of something happening, or this state being possible? Probability. So I assume that nobody's had statistics here, but one of the premises of statistics is the larger the number in your population, large numbers of atoms and molecules, the better is your statistical estimate of what state and what conditions will be. So that's why large numbers are better for statistical reasons. All right, all of these particles are in random motion, right? They're moving from here to there, and depending on whether it's a solid, liquid, or gas, they encounter one another occasionally. Now, the kinetic energy of each one of these particles, if we knew the particle, where it was, how fast it's moving, what its mass is, then we could calculate how much energy each one contained, right? All you need is this formula. Kinetic energy is 1/2 times the mass of the particle or the object times the square of its velocity. And that is the kinetic energy of that particle or that bowling ball. You know, it works for any size. It works for planets and moons. The kinetic energy is established by this formula. Okay. So we have random motion and lots of particles, tiny particles, right? Some of them can be visualized with the proper equipment, but for the most part, we can't see them. These particles interact with one another. As they approach, right, they either attract or repel, depending on the nature of the particle and its orientation when they impact one another. Now, let me see. Let me get my hard copy out so I can make this flow a little better. No, that's not it. Where is it? Hold on a second. I want to get my hard copy. Okay, here we go. So I keep track of the discussion so it'll flow better. All right. Now, we understand that matter interacts. I mean, that's just a given. When particles approach one another, they either repel or they attract, and that influences the amount of energy that's contained in the matter, right? Because if there's a strong attraction between the particles, it's going to be more difficult to pull them apart. Say you need more heat to change a solid from to a liquid, because you have to break those bonds. If they repel one another, then it makes it easier to phase change from a solid to a liquid to a gas. But the kinetic molecular theory, in its purest form, assumes that the particles do not interact. This is called an ideal. In the beginning, it was called an ideal gas. But an ideal liquid and an ideal solid, you have to tweak the theory a little bit to account for that. But for gases, we assume that there's no interaction. That's an ideal gas. And when these particles approach one another, they behave like billiard balls. They just bounce off, right? Perfectly elastic collision, which means that all the energy coming in, the kinetic energy, is transferred back out to the particles, and they head off in other directions, with the total kinetic energy of that collision being preserved. Of course, with liquids and solids, we know that those interactions exist. Otherwise, you would not get a liquid formed from a gas as you cool it down. You have to have the interactions. So this energy that is attributed to attractions and repulsions is potential energy. It's stored energy in the matter, and it depends upon what position that all the particles are in, what is their chemical makeup, their composition, and how are they oriented to one another to maximize attraction. And generally speaking, in fact, this is a maxim in chemistry. During any process, whether it's physical or chemical, the components of the mixture that's undergoing in the system, let's call it a system, everything inside the system that you've defined tends toward the lowest possible energy. They want to roll down the hill into a valley and stay there. And that's total energy. So potential energy is only one component. Kinetic energy is one, right, that you can measure by how fast they're moving. Potential energy is just that. It's the potential. How much energy is stored in these interactions. And we determine that by how much energy is required to break those bonds. Electrostatic interactions tend to be very strong, right? So in an ionic solid like sodium chloride, you have sodium ions and chloride ions interacting, right, electrostatically, but you have lots of these around here, right? And you have another one on the other side of that board and one in front. So there are actually 6 chlorides surrounding each sodium. And you have sodiums here, like that. So you have 4 sodiums surrounding that chloride, and then a sodium behind, sodium ion behind, and sodium in front. So for every chloride, there are 6 sodiums. So what I'm saying is the formula for that crystal lattice would better be expressed as 6 and 6. But of course, we go for the simplest whole number ratio. And for all ionic solids, that's true. Regardless of what their crystal structure is, you go for the simplest. So that's why we only write it that way, 1 to 1. But this electrostatic interaction, this attraction, is very strong. So there's a lot of potential energy stored in that, at that level. And the way you measure it is you add energy to it in the form of, usually in the form of heat, by raising the temperature, and say, at what point does that sodium chloride melt from a solid to a liquid? Then you've initiated the first step in breaking those bonds, right? They're not completely broken because they can move past one another and they still interact. So if you want to break the bonds completely, you will go from the solid you will go from the solid to the gas and individual ions in the gaseous state. So how much energy does it take to go from that to that? We'll tell you. It's got a special name. That's a TT, lattice energy. So that's the lattice energy. How much energy does it take to break that bond and make gaseous ions out of it? Actually, lattice energy is the other way around. You take the ions and you let them condense into a solid, and then how much energy comes out, right? Because if energy is leaving the system, that's an expression of going from high energy state to a low energy state, and the energy comes out. And that's the measurement of this lattice energy. And that tells you how strong is the bond. All right. So we're still in the kinetic molecular theory. And that's one type of interaction, the electrostatic attraction. There are weaker attractions if there are no charges, but perhaps your molecule is polar. That is, the electron density for the molecule is slightly shifted to one side of the molecule. Water is a perfect example. Right? These bonds are polar. That is, oxygen pulls electrons closer to itself, but it doesn't completely remove them from the hydrogen. So it tends to give you an electron density like that. So you have negatives on this side, positives on this side, right? So that gives you an overall polar molecule. And that's the way we draw this, called a dipole arrow. So you write that, and it says, okay, it's negative this way, positive that way. So what you get is that very slight difference in, that's what the little delta means, slight negative, not a complete negative. And with that polarity, when these molecules interact, another water molecule might come in here with a negative down here and be attracted. Right? That's called a polar bond. In fact, this is a special kind of polar bond called the hydrogen bond. And that's another way that these molecules can interact. Now, the ionic solids are permanent charges. And these are permanent dipoles. But there are other types of electron distributions that occur for a nanosecond and then they're gone. And we won't beat that horse right now, but just recognize that there are always shifting electron densities which give small changes in charge that can be used by molecules to form attractions. So this is a dipole. I might as well just name the other one. The others are called London dispersion. And you can get these. In fact, these are always present in molecules. It's just that they're so small. If you have others like dipoles or ionics, then they're swamped, right? They don't really matter. But if you don't have the dipole and you don't have the ionic available, then the London dispersion forces are still there. And I'm not going to take time to describe them right now. So we may come back to them later. If not, then just file that away and hopefully it'll help you understand that there are a number of different ways that atoms, molecules, ions can attract one another. Okay, so how do we get this kinetic energy of molecules to change? One way is through the addition of energy and a change in temperature. So if you change the temperature, say you increase the temperature of your matter, whether it's a solid, liquid, or gas, then you will increase the kinetic energy of the particles in that system. And in fact, temperature is a measure of average kinetic energy. Okay? Remember, we've got large particles, large numbers of particles, but they're not all moving at the same velocity. Right? And if it's not a pure substance, say it's a mixture, then of course the heavier ones for the same energy will be moving slower, right? Based on this, 1/2 mv squared. So if they've got the same energy, say two particles, like this one and that one, if they have the same energy, then the smaller one with a smaller mass has to be moving faster. The bigger one with a larger mass can be moving slower and have the same kinetic energy. So temperature is a measure of the average kinetic energy for all the particles in your system. Now, when they bounce off of each other, here's that reference to the ideal situation, right? The ideal is that when particles interact, they transfer energy at the moment of impact. They transfer energy into some other form, say compression. But when they leave one another, they take all of that energy with them. That's an elastic collision. That's one in which all the kinetic energy that goes into the collision comes out of the collision. Like billiard balls. Right? When you smack a billiard ball, that's a pretty good example of an elastic collision. Or I don't know if they're popular anymore. We used to call them super balls. They were hard rubber balls made of a specific material and constructed in such a way that if you dropped it on the floor, it would come back up and almost come exactly to the same height, which means all that energy from position transferred into velocity at the bottom. When it hits the floor, it gets all that energy back and reverses direction and comes back. Now, they're not perfectly elastic. They're maybe 90 or 95%. But that's the best example I can think of outside of billiard balls that of an elastic collision. Now, since we're on the topic, what would an inelastic collision be? Well, first of all, I made reference to energy transfer from height to the floor. That's positional potential energy. But an object that's a certain height above the Earth's center has acquired energy. In other words, you have to put energy into it to get it up there. It's like you walking upstairs, right? That's an exertion. You're putting energy into your body to go from a lower position to a higher position. Now, how do you get that energy back? Well, one way is to jump off the building. And all that potential energy that you had up here potential energy, you'll get it back as kinetic energy at just the moment before you hit the ground, right? And your kinetic energy will be equal to the potential energy. And it can be calculated, right? There's one formula for that one and one formula for this one. Set them equal to each other. But when you hit the ground, what type of impact will you have? Well, you'll bounce a little bit, but you're not going to bounce back up to this height, correct? That's an inelastic collision. In other words, when you hit the ground, most of that energy that was kinetic energy right before you hit the ground is converted into heat and broken bones and damaged organs, right? Energy goes into your body and breaks bonds. So sometimes that's broken bones, sometimes that's destroyed tissues. You'll bounce a little bit, but not much. So that's an inelastic collision. You don't get the energy back as kinetic energy and bounce back up to this height. Okay. So the differences among solids, liquids, and gases can be explained in terms of the kinetic energy and the potential energy of the substance. These attractions, and we're generalizing as electrostatic attractions. It could be ions, or it could be those polar molecules. Those are all electrostatic. Those are referenced as potential energy. The kinetic energy, of course, is related to motion, which we can measure as temperature. So the average kinetic energy of your substance is temperature, registered as temperature. And this kinetic energy is considered a disruptive force. That is, it tends to make the particles stay apart, independent from one another. Whereas the potential energy is a cohesive force, which tends to draw them together. So we can think of matter as a competition between kinetic energy and potential energy. Kinetic energy versus potential energy. This is a potential energy is a cohesive, contributes to cohesive forces. And kinetic energy is disruptive. Okay? If we view matter in its various states in these terms, we can make some predictions about which one is dominant. So the two types of energy are kinetic and potential energy. Right? So for solids, the physical state is characterized by potential energy being predominant. This one, for solids. Because they're held together. They have very low kinetic energy relative to their potential energy. That's why they stay in that form. And it tends to fix the position of each of the molecules, atoms, ions in that solid. Now, they do have some vibratory motion, right? Back and forth. So that is motion, and that's kinetic energy. And it tends to, it's trying to disrupt the solid structure, but it's just not enough to overcome the potential energy holding it together. Okay, so this is the artist's rendition. This is, you can see they're vibrating. And solids will have a a certain amount of vibratory motion based on their temperature. So as you increase the temperature, the vibratory motion increases. And that is fighting those cohesive forces, the potential energy. And once you reach a point where the kinetic energy from vibration exceeds the cohesive, then they fall apart into a liquid. We've talked about this earlier. I'm not going to stop on this one. Well, okay, this is explanation in terms of kinetic and potential energy, right? So strong cohesive forces hold the particles together in this fixed position. That makes them hold their shape. That also gives them high density because they're held closer together as the kinetic energy is trying to disrupt them, but they're still held close together. And many of them are actually touching. So that says for density, you have large numbers of particles with their masses confined to a small volume, which means high density. It also means small compressibility. Compressibility is attributed to how much empty space is there, right? There's not much empty space in a solid. So when you push on it, there's no place for it to go. It can't compress without changing its structure, right? The crystal structure of, say, sodium chloride, there are empty spaces in there, right, between the molecules. They can touch at their extremities, right, stack them this way and that way, and there's still empty space in there. So if you put them under enough pressure, they'll shift a little bit to minimize that empty space. But it won't be much because there's not much there. Thermal expansion is not very high for solids. It's measurable, but it's not very high. Why? Because thermal expansion is due to introduction of kinetic energy and vibration fighting these cohesive forces. And as you increase the temperature, they tend to vibrate more, but they don't move very far apart, right? They don't create any extra space. Okay, for liquids, the potential energy and the kinetic energy are roughly equal, right? So solids are dominant over here. Liquids have more or less a balance between kinetic and potential energy. Okay? They're close to one another, but there is a little bit more space. And they have, not only do they have vibrational energy, but they have also disrupted some of these bonds attributed to potential energy, and they're able to slide past one another. So they need more space. That's why liquids are generally less dense than solids. There are exceptions, right? Water is one of them. When water freezes from a liquid to a solid, it expands. But there's a special reason for that. I'll talk about it later, hopefully. So they're still in constant random motion, but they tend to slide freely past one another because this has been reduced, this has been increased. So now they're roughly equal. And that's why liquids require a vessel to hold them. Because if they can slide past one another, they can slide out onto the table. And that's what we're talking about here. They have a definite volume because they're still attracted enough so that the empty space is maintained. It shifts. The empty space shifts with the position of each of the molecules, but the total, the average empty space remains constant. They have a general high density, comparable to, but somewhat less than the solid in most cases, because they're still touching one another. They're just moving past. Right? The kinetic energy is enough to disrupt those bonds enough where they can move past one another. So in so doing, they cannot maintain their volume, but they're close enough to maintain their density. So they have relatively high density. And because there's not a whole lot of empty space, they're also limited in compressibility. They're a little bit more compressible than solids, but not much. They have a very small thermal expansion. They're still being held together by these forces. So when you add heat, they won't expand very much, because what you need for expansion is space. And you get space by moving particles farther apart. And the only way you can get them farther apart is to increase their kinetic energy. Make them move away from each other rapidly before they impact another one. Okay, gases. Now we're getting to the point where kinetic energy is dominant over potential energy. I mean, it's extreme. Kinetic energy. These cohesive forces are virtually non-existent for gases. So at relatively high temperatures, and I say relatively, based upon 0K, right, above absolute zero, room temperature will be 200 and, let's see, 25 and 273 is 298. 298K is high temperature. So you've got a lot of kinetic energy in a gas. And potential energy is non-existent. And there's lots of space between them, extreme amounts of space. In fact, an ideal gas is treated as if the particles are not even there. What does that mean? Well, in practical terms, that would mean an ideal gas, if you squeeze it, it will stay a gas all the way down to nothing, zero volume. That's the ideal gas. Of course, we know that doesn't happen because there are particles there, but there's so much space between them, you can treat them as if there are no particles. And that's because they don't attract one another to any significant amount. Kinetic energy is overwhelmingly dominant. And so that's why gases must be contained. For their volume, they have to be contained three-dimensionally. That is, the vessel must be sealed to establish the volume of a gas. And this is repeating what I just said. And now, density, remember, density is due to mass divided by volume. So if you have a definite volume, and the mass is related to the number of particles, and if there's a lot of space in there, that means there are very few particles. So there's very low mass. So density calculation for a gas is going to be a very low number because of all this empty space. They have very large compressibility, and that's attributed exclusively to the fact that there's lots of space. Right? You still got the same number of particles here, but you can squeeze them together and you still have lots of space. Right? Okay, so that explains their compressibility. They can be pushed closer together simply because there's lots of space. They will expand thermally if you increase the temperature. All other factors being the same, like the gas is under a certain amount of pressure and that pressure doesn't change, then as you heat them up, they will expand. That is, you're increasing kinetic energy of the particles, and they need more space. And of course, you don't change the mass, right? Kinetic energy. You increase the temperature, you increase the kinetic energy average by increasing the velocity. The mass doesn't change. So the velocity has to explain the kinetic energy. And when you increase the energy of the particles by increasing their temperature, what happens? Well, they smack against the walls. They hit the walls harder. And if one of the walls is movable, they'll hit that thing hard enough to move it up against that constant pressure. So when you change the temperature, that's why the volume increases. Physical states, there you go. Gases, liquids, solids. Now we're going to sort of regress. We actually went backwards. We talked about the theory first before we talked about the laws. In general, laws come first, and then you develop theories to explain why the laws work. But I'm trying to be faithful to the authors of the textbook, and they put them in this order. Now we're going to talk about the laws that led to the development of the kinetic molecular theory. And we start with gases. We start with gases because that's the order in which modern science began to develop theories about matter and chemistry. It started with gases because their equipment, their technology was at a state where the study of gases was favored. The study of solids and liquids was more like, it was still in its alchemistry stages, right? It was more like recipes, right? We didn't understand. We knew how to do things, like alchemists know how to dissolve various minerals in strong acids. They knew how to do that, but they didn't know why. And there was no study of solids and liquids at the beginning of the modern age in scientific terms because the technology wasn't there. So we started with gases. So remember what a law is. A law only says this is what happens. If you have these conditions, then the law says this will happen always, every time. It's only the theory that explains why. And we've already covered the theory. So maybe the theory will help you understand why the laws act the way they do. That's the hope. So when we're describing a gas, let's say with the physical state of a gas, we need 4 conditions. We need to know, let's see, I'll put them in the same order there. We need to know the amount of gas that I designate as moles, right? How many particles are there? We need to know the pressure on the gas. We need to know the temperature of the gas. And we need to know the volume. Those 4 measurements completely describe the gas. And the other thing that is that made the study of gases particularly attractive was that gases tend to behave the same way no matter what the particles are. Are they composed of oxygen, nitrogen, chlorine, hydrogen, helium? It doesn't matter. Why? Because an ideal gas doesn't interact. So it doesn't matter what the particles are. and they're very far apart. So you can treat them as if the particles aren't even there. So the study of gases was particularly attractive because you could confine air in a vessel and study it, or you could confine oxygen or nitrogen in a vessel and study it, and you get the same results, no matter what the gas is. Okay, we need to define some terms, right? We know what temperature is, and it's generally in terms of K, Kelvin. For gases, whenever you're talking about a gas, you always have to convert the temperature to Kelvin. So if the problem gives you temperature in degrees Celsius, you must convert it to Kelvin, right? And remember, Kelvin is equal to degrees C plus 273. And that's the formula. If you know this one, you can get Kelvin from that. If you know Kelvin and the question asks you what is the final temperature in degrees Celsius, then once you get Kelvin, you got to convert it back. So you say Kelvin minus 273, you get Celsius. Now for pressure, pressure by definition is force applied over an area, right? So if we apply a force of, let's see, forces in terms of newtons. If we apply 1 Newton per square meter, that will be the standard, the SI standard for pressure. Because Newton is an SI unit, meters is the standard SI unit. So square meters and newtons would be the force per unit area. Now, this is given a special name. That's abbreviated for Pascal. It's named after a scientist, mathematician. Actually, he was a polymath. Pascal that, well, he's just given credit, and they named this unit after him. But that's what it's equal to. But there is some historical baggage to be considered when we talk about pressure. That may be the standard, and it's interconvertible with other measurements of pressure, but measurements of pressure were developed using other types of units. One of those units is the atmosphere. 1 atmosphere. That's the pressure on average experienced at sea level. 1 atmosphere, right? So we had to fix its conversion because we know that atmospheric pressure changes, right? So 1 atmosphere then has to be fixed relative to other measurements. And one of those measurements is millimeters of mercury. Now, what does that mean? Well, millimeters of mercury is based upon the development of a measuring device called a barometer. It was invented by Torricelli, and for that reason, it's also referred to as 760 Tor after Torricelli. So these are equivalent to one another. Now, the development of the barometer, let's see. Let me see if there's going to be a discussion about it, so I won't steal my own thunder. Yeah, I'm going to talk about it. There's a slide for it. All right, so we'll talk about the development of the barometer in just a minute. Other units of measure. Well, if we measure pressure in imperial units, English units, then the force would be in pounds per square inch. And 1 atmosphere is equal to 14.7 pounds per square inch, PSI. Okay? Hold on a second. Come on. All right. So these are various measurements of pressure. When you take the tire gauge, stick it on your tire, and check the pressure in your tire, it's calibrated usually in pounds per square inch. Some of them now have dual measurements. They might give it to you in I don't know. There are other units that they can use, but they all have pounds per square inch in this country. The pounds per square inch is actually force per unit area, right? SI units, actually this is not true. Kilogram is a mass. It's not a force, but it can be related to an actual force, newtons. Should I mess with that or not? Yeah, might as well, to be thorough. So this is, if this is the standard, how do we relate kilograms to newtons? Well, we go back to Newton's second law of motion. This is area. This is acceleration. Acceleration is measured in meters per second. That is, how does the velocity change over time? So this would be in terms of meters per second squared. Okay, that's acceleration. Meters per second is velocity, and if the velocity is changing every second, then you have another term, a second term down here. Mass is in kilograms. Okay, standard units. So if a mass is accelerated at a given rate, it requires a certain force, and this force is the Newton. So 1 Newton is equal to 1 kilogram meter per second squared. That's the relationship of kilograms and newtons. Now, on the surface of the Earth, this acceleration here is a special term called g. And that acceleration is 9.80 meters per second squared. That's the acceleration due to gravity. So if you plug those values in here, then you get the equivalence of newtons. Okay, so that's not something that I'm going to hold you to. I just wanted to explain the relationship. When it says kilogram per meter squared, that's not accurate, because in order to be force per unit area, you can't use kilograms. You must use newtons. But it's still a valid expression, kilograms per meter squared. And if you're on the surface of the Earth, then the kilograms are constant, and you can use it in calculation. It's just, I want you to recognize that it's not really an expression of pressure in the strictest definition. Okay. So let me erase this. I'll probably have to write it again later, but I'll leave those up there because these are the descriptors for gases. We're talking about pressure right now. So how do we know that there is force inside the vessel of our gas? Well, you can stick a pressure gauge on it and it'll measure force per unit area. Or if you have a piston in a cylinder, you can push on it and feel it pushing back. So you know the gas in there is applying a force. It's under pressure. Now the barometer was developed by Torricelli. I'm trying to remember when it was. First of the 17th century, I think. But what he did was he took a tube of glass, and here we're talking about technology. At this time, at the beginning of the Renaissance, glass blowers were very good at producing uniform diameter tubing. They had figured that one out. So Torricelli went to his neighborhood glass blower, and he got a tube of uniform diameter and closed at one end, open at the other. And he took it open end up, and he poured mercury into it, all the way up to the top. And he capped it with his thumb, and then inverted the glass and submerged his hand in the pool of mercury and turned it loose. Now, before anything happens, that tube in mercury, right, is filled, right? So it filled to the top with mercury. When he turned his thumb loose, what happened? The level of mercury dropped. So it came down to here. So if this is the level of mercury in the vat, then the difference between here and here at sea level is 760 millimeters, which is 1 atmosphere. Okay? Now, what do we have up here in that space? That's a vacuum. That was the first vacuum produced in a barometer. Now, we know that mercury as a liquid is slightly volatile. So there will be some mercury atoms floating around up here, but for all intents and purposes, it's a vacuum. All right. So now we have a way of measuring pressure. First, they used it for air pressure. Right? Just take your barometer. Oh, by the way, why did Torricelli use mercury? Why didn't he use some other liquid, right? Well, mercury was common, of course. It was a metal, so it was very dense. I think it's in the neighborhood of 13.5 grams per cubic centimeter. If he had used water in his barometer, a simple calculation, water is 1 gram per cubic centimeter. If he had used water, his glass tube would have to be in the neighborhood of 33 feet long, right? That's unwieldy. So he reasoned with a denser liquid, he could use a shorter tube. So that's what he did. Okay, so what else did he do? Well, he took this barometer and he threw it in the back of his ox cart and he went up the mountain, nearest mountains. And he found that the higher he got, the lower the mercury dropped. And he reasoned that the force of the atmosphere above on that level was pushing the mercury up. So there's nothing up here holding it. So the only thing holding up was the force on this surface. the air pressure was decreasing with altitude. And he reasoned that's because that there's less atmosphere above me when I'm on top of a mountain. And he went down, he took the barometer and checked the measure at several hundred feet wherever he lived. And then he went down to the ocean, sea level. And it went up to something near 760 millimeters. All right, so your altitude determined the height of the mercury column. Other people noticed that if you just let it sit on the bench and you took measurements day after day after day, you could correlate that with weather changes, right? If the weather was getting bad, clouds rolling in, you got a storm on the way, the level of mercury would drop. Low pressure. Once the weather got better and the sun started to shine, pressure went up. High pressure. So they began to associate low pressure, high pressure with bad weather, good weather, respectively. And that's still done today. Only they use a different measure. They use the millibar as a measure of pressure, and it's interconvertible with these units. You just need a conversion factor. All right, so what are the four variables involved in gas laws? Pressure, volume, temperature, and moles, the amount of gas. And when we say amount, we don't mean mass, we mean moles. All right, so our first law. And what have I got? 10:24 to 11:50. Oh, okay, I've got time. Is that right? No, 11 o'clock. I was looking at the wrong one. 11 o'clock means I've only got, I got less than 30, I've got a little over 30 minutes. All right, we'll try to get through this. Boyle's law. Okay, Robert Boyle was an English scientist, and he's given credit for the first quantitative approach to investigating phenomena, both physical and chemical. And this is one of the things that came out of it. Boyle's law relates pressure and volume of a gas. Now, remember, I'll point this out. If you're investigating the relationship of this one to this one, then these have to be constant. You have to be sure that the temperature and the number of moles is constant. Then you can let the pressure and volume vary and see what the relationship is. Well, Boyle's law, strictly put, is pressure volume equals a constant value, right? And that constant value will change depending on your experiment. Boyle did it with a J tube. Let's see. Yeah, it's not in the slide, so I'll draw a picture. What he used was a tube like this. And remember, glass tubing of uniform diameter was easy to make. And what he did was he added mercury in here. And in the beginning, mercury just pulled up on the bottom right there. And then he added a little more, and eventually it touched the inner wall of that curve. And when it did, that trapped gas inside the end of that J tube. So now you have fixed moles right there. Now, how did he maintain constant temperature? Well, over the duration of an experiment, room temperature is not going to change that much. If you're really concerned, you just submerge it in a water bath, because water doesn't change temperatures very much as the heat in the room changes. Or you could even dump a bunch of ice in it, and then you know it's exactly 0 degrees centigrade. That's a better way to do it. Okay, so what did he do? Well, he kept adding mercury. He noticed that as he added more mercury, the level in here didn't go up the same as it was out here. So he reasoned that the pressure on mercury in there, pressure on the gas in there, was the difference between height. That difference in height was a measure of the pressure on the gas. And then the volume, this is the height of the mercury. This would be the height of the gas. And since the tube is uniform diameter, then the volume changes with the height, right? Height times area is volume. So if he measured the height, then he knew that he had a given volume. And if he wanted to, he could just take the diameter of the gas, calculate the area of the cylinder in the gas, and calculate the area, right? And relate pressure in millimeters of mercury to the area of the gas. And he noticed that as the pressure increased, the volume decreased, right? Pressure increases, volume decreases. Whenever you get a product of two variables equal to a constant, these variables are related inversely. As one goes up, the other has to go down. Okay, so that was Boyle's experiment. And this was the result. Now, you notice that at any one time, measure the pressure and the volume, it's equal to a constant. During that same experiment, when you measure the pressure and the volume again, it's equal to that same constant. So what's the cumulative law? No, it's not the cumulative. It's a mathematical. It escapes me for the moment. What I'm saying is, if A is equal to B and B is equal to C, then A is equal to C. So we can get rid of that constant, and those two are equal. So this is what I call the before-after approach to problem solving. You know the conditions before, and you know one of them after, you can solve for the third unknown. All right. All right, so this is the artist's rendition. You know, as you decrease the volume, you increase the pressure. And the reason for that is, according to the kinetic molecular theory, increasing the pressure is required because as you confine the gases at the same kinetic energy, constant temperature, they've all got the same kinetic energy, they're going to apply more force over a smaller area. So that's why the pressure increases as the volume decreases. All right, so there's Boyle's law in a before and after formula. And we're kind of short on time, so I may have to just reference this solution to the problem. The key to working these problems is put the numbers in the right variables. What is the starting pressure? A sample of helium gas occupies 12.4 liters at 0.956 atmospheres. That's starting conditions. And that's why I tend to write those things on the board, separate from the word problem. You may even say like this: initial, final. So these two multiplied together equals those two multiplied together. So initial pressure is 0.956 atmospheres. Volume is 12.4 liters. Pressure afterwards, what volume will it occupy at 1.2 atmospheres? So we're increasing the pressure to 1.2 atmospheres, and there's your unknown. Now, if you set it up like that, you're sure that your values are going into the right place in the formula, right? If you put the volume over here in the wrong place over there, you get the wrong answer. That's why I like to extract information from word problems into this form. Then you know what you have and where it belongs. All right, Charles' law. Charles came along several decades later, and Charles was able to do his experiments, and Charles is a Frenchman, was able to do his experiments because a reliable measuring device for temperature was developed between Boyle's and Charles' time frame. So they had a reliable thermometer that Charles could use to measure temperature. So if you're going to let temperature and volume vary here, these need to be held constant. Temperature and volume can vary, but the others have to be constant. And temperature must be in Kelvin. There's a scientific explanation and there's a practical explanation for why temperature must be Kelvin. The practical explanation is this: what happens if you use degrees C? Well, on that scale, you have negative numbers. If your temperature drops below 0 degrees Celsius, you're into negative numbers, and then you've introduced a negative term into the expression, and your volume might come out negative, right? That'll never do. You can't have negative volume. So a new temperature scale is needed, and Lord Kelvin came up with that schedule, that measurement. And now all values of Kelvin are positive. There's nothing below 0. So every value is positive. That way, this expression will never have a negative answer. Okay, so that's Charles' law. When I was in school, I learned the possessive, if there's an S on the end of the word, you just add an apostrophe, and that makes it possessive. But sometime between when I went to school and now, they said, oh no, you have to add an S after everything. You know, I think it's stupid, but that's the way it is. Charles' law relates volume and temperature. Oops, excuse me. Wrong relationship. Volume and temperature is a constant. So whenever you have a quotient, not a product, but a quotient of two variables equal to a constant, you have a direct relationship. That is, volume goes up as temperature goes up in order to maintain that constant, right? If volume went up and temperature went down, it wouldn't be constant anymore. So that's a direct relationship. And for the same reason, A equals B and B equals C, so A equals C. That's our before-after scenario for relationships of volume and temperature. So why does the volume increase as temperature increases? You increase the kinetic energy of the molecules inside the container. When you change the temperature, increase the temperature, more kinetic energy, which means when they smack the walls, they're hitting harder. And that means if the pressure is constant, the inside increase in velocity, force, means that against that constant pressure, the volume increases until you thin out the gas enough so that the impacts of those molecules at higher temperature balances the external force, the external pressure. At that point, then you have the second relationship. All right, that's Charles' law. So if we have this one, I know I'm going to run out of time. So we'll just say, all right, if you have a balloon that contains 1.3 liters of air, and the temperature is 24.7 degrees centigrade. What's the question? What's the volume of the sample if the pressure is constant? What's the volume of the sample if we change the temperature? Yeah, we're going to drop the temperature to minus 78.5 degrees C. What's this one? Now we have everything on the board, and we know with Charles' law, you got to change it to Kelvin. So you just say plus 273, plus 273. That gives you a temperature that you can work with. Then you plug it into Charles' law. So here's the temperature changes right there. And we solve for the unknown. We find out if you decrease the temperature of this gas in the balloon from about 25 degrees room temperature down to minus 78.5 by submerging it in liquid nitrogen, then you get a decrease in volume. If you used these values, well, to make a long story short, you get a wrong answer. All right, so that's Charles' law. Now, we can combine these laws. And what we've done here actually is, we left out one law. I guess the authors didn't think it was important. I'm going to mention it, Avogadro's law. Avogadro's law is actually more important than the other two. And hopefully I'll be able to offer that explanation at some point. But in Avogadro's law, we relate number of moles and volume. So these must be constant. Constant pressure, constant temperature. And if you increase the number of moles in the vessel, the volume will increase. Okay, So they're directly related. Oh, sorry. There. Moles and volume. So if you say this and this, there you get before and after. Now for this combined law, and I need to correct that slide because this is very important. For the combined law, we say, how are they related? Well, if we take them one law at a time, we would say pressure, volume, pressure, volume. Okay? Now, how is volume and temperature? What's the relationship there? Well, temperature is related like that. Right here. So if pressure is constant in these situations, then you have Charles' law. But we also have a relationship of Avogadro, volume and moles. So you could have a moles here, volume, moles, volume, moles. So this is the combined gas law. And all you have to do to get any one of the other laws is just to hold two of them constant. Right? If we hold, we haven't discussed this one yet, but if you hold pressure and volume constant, then the relationship of moles and temperature is inverse. Is it? I think about that one. But what you can do with the combined gas law is if multiple variables are changing, then you can use the combined gas law to give you an answer. All you need is one unknown. If you have factors, if you have values for each one of these, and only one of them is unknown, you can solve for it. That's math. So in this case, we're only interested in pressure, volume, and temperature. And the only variable that is unknown is the final temperature. So there it is. This is in Celsius plus 273 in this formula, and you find out that under these conditions, if you change the conditions from this side to that side, you change the temperature to 696 degrees from its starting point of 27 degrees. Now, up to this point, we've talked about purely physical changes, right? There's been no chemistry here. But we can apply these gas laws to chemistry if we have changes in the gas during a reaction. For instance, if we have nitroglycerin in a vessel and it decomposes, it produces a huge amount. It goes from no gas to 29 moles of gas, like that. That's why nitroglycerin is so powerful. It just decomposes into those gases, and all that increased pressure is a force in a confined space that blows things apart. So there's a chemical reaction, and we can relate the before and after, knowing the mole relationship, the stoichiometry of the reaction. I don't have that formula up here for you, but hopefully we'll get to it at one point. Now, everything up till now, we've discussed in terms of before and after. You know the conditions before, then you make a change. But what if you're in a state situation? What is the present state of the gas? And we know 3 of these, we don't know the 4th one. What do? Well, we have this relationship of pressure, volume, moles, and temperature is equal to a constant. Right? We know that based on the combined gas law. That's true. Well, if you know the units of measure for each one, say this one's atmospheres, this one's liters, this one's moles, and this one is K. And you make those measurements, right? You measure what these are under certain conditions, and you can do it you can change conditions and measure it. We end up with a value over here that's 0.08206 liter atmospheres per mole K. That is a constant, and it's known as the ideal gas constant, which is applied to, and we give it a special symbol, R. Rearrange it, and it usually looks like PV equals nRT. So there's your constant. These are your 4 variables. Now that you know this constant, and it's important that if you're going to use that constant, that your units for each of the others has to be liters, atmospheres, moles, and K. If it's anything else, that constant won't work. Okay, and there are several R constants that are developed depending on the situation. But for our purposes, we're going to stick with this one. So that's what you do if you don't know the before to get to the after. If you're stuck in the after, the present state, then you use this one. So problem solving technique, you look for what type of problem is it with gases. Are you given before conditions and after with a missing variable? Or are you given a state situation? If it's the state, you use this formula. Now, standard temperature, in case you need to know, for gases, when you're talking about physical changes of gases, the standard temperature is 0 degrees Celsius, 273 K. The standard pressure is the same for any reaction, 1 atmosphere. So when if the problem says under standard temperature and pressure conditions, that's what it means when you're talking about gases, 0 degrees centigrade. Come on. All right. So let me see, how close are we? We're kind of far away from our stopping point. Let's see, we've done that, We're there. There's an ideal gas problem. So there's the solution, right? This is a state function. This is a state situation. So you're given information here. The pressure inside your tire is this many atmospheres. That's the volume of your tire. There's your gas constant. There's the temperature. And you solve for the number of moles. So now we can say how many moles of air are in my tire under these conditions, 2.24 moles. Now, where would we use that? Example. If you need to know the molar mass of a compound, right? You need to know the molar mass of your compound, but you don't know what the formula is, right? You haven't determined that yet. You may have analyzed the percentage composition of each of the elements, but you don't know what the formula is, right? So in order to determine the molar mass, you have a mass and you need to know the number of moles. So if you know the mass of the gas and you determine these other values for that confined gas, pressure, volume, and temperature, then you can calculate the number of moles of gas that you have in that container. Plug it in that formula with this mass, and you can determine the molar mass of the gas. My general chemistry class does one of those determinations, one of their exercises. Wait a minute. We may be doing, do we do one of those? Hold on a second. No, we don't. Not in this class. We do molecular weight, but we do it by titration of an acid. Okay, that's a practical application. Let's see. Similar. What do we want to know here? We know the pressure inside the tank. And we're not given before and after, so we have to use the state function, the ideal gas equation. Now, let's see. We got a few more minutes. Can we get through? Yeah, this is the last one. Dalton, John Dalton. Partial pressure. Okay. You may remember Dalton proposed the atomic theory, right? But he did other things. And this is one of his more useful equations. What Dalton said is that when you have a mixture of gases in a container, you can measure the total pressure. And if there's some way that you could measure the individual pressures that are contributed by each of the different gases, so you have nitrogen, oxygen, and argon at sea level, the total pressure is going to be 1 atmosphere. That 1 atmosphere is a summation of the partial pressures contributed by each of the other gases. So this would be due to the pressure due to nitrogen, plus the pressure due to oxygen, plus the pressure due to argon. Those are the 3 major ingredients of atmosphere. There are some minor components, but they're not going to influence our results very much. If you knew the partial pressures of each one of these, it would add up to 1 atmosphere. Or if you knew 2 of them, you could find out what the third one was, if the total is 1 atmosphere. So at sea level, well, the composition of gas is nitrogen is 0.78 atmospheres. And oxygen is 0.2 atmospheres. And argon is 0.01 atmospheres. Add those up, you get 1 atmosphere. That's what Dalton says. Mixtures of gases will produce a total pressure based upon the individual partial pressures, the summation of the partial pressures of each of the gases. And it doesn't matter how many you have. I mean, whatever it takes. So if the pressure here is measured at that value, and pressure here is measured at that one, pressure here is measured at that one, when you put them all together, you get a total of 6, right? 2 plus 3 plus 1 is 6. Very simple. Now, why is that? The reason for that is based upon constant pressure. Constant temperature and constant volume. The relationship is between pressure and moles. So as you increase the number of moles, the total pressure. Well, what's the contribution? Well, you've got so many moles here and so many moles there and so many moles there of each one of these. They're fractional molar contribution, designated as mole fraction with that fancy X. is equal to 0.78. That's the mole fraction of nitrogen in atmosphere, 0.78. If you have 1 mole total gas, 0.78 of it will be nitrogen if it's air. 0.2 will be the fraction of oxygen. So it's all based upon how many moles you have. When you put more moles together, you get an increase in pressure. And Dalton says that increase of pressure is due to the partial pressure here based on its mole fraction, et cetera, et cetera. So let's see what this one says. If you have oxygen, helium, and nitrogen with a total pressure of 780 millimeters of mercury, what's the partial pressure of oxygen if the partial pressure of helium and nitrogen are 86 and 124 millimeters respectively? You just subtract these two from the total and you get oxygen. It's 570 millimeters of mercury. Okay? It's really very simple and powerful, as a matter of fact. All right, we've got this problem, which can be solved using Dalton's law of partial pressures and Boyle's law. So the question is, if we have this container and it's at constant temperature, it tells us what the temperature is, but if it's at constant temperature, what will be the pressure of the gas inside the container after the valve is opened? All right, let's take a qualitative look at this. You've got 2 atmospheres pressure here and 3 atmospheres pressure there. Which way is the gas going to move? When you open the valve, it's going from the smaller one to the larger one until the pressures are equalized. So the pressure should be somewhere between 2 and 3, the total pressure. Now, how do we attack this problem? Fortunately, we can treat the gas in this one different than the gas in this one. So if we take the gas in this big one and say, suppose there's nothing over here, it's just a vacuum. Then if you go from this one to a larger volume, that means you can use Boyle's law to determine the partial pressure contributed by this gas. Then you go and say, well, let's say, what if this is a vacuum? What happens here? Open the valve, and this one goes from this volume to a total volume, right? And what's the total volume? It'll be 12 liters for both of them, 3 plus 9. Then you can calculate the partial pressure due to this gas. Now that you have the partial pressure of this one and that one together physically in the same 12-liter volume, add them together, that will be your total. And here's the problem worked out. There's the final volume. There's the final pressure. This is before and after. This is for the larger vessel. So the larger vessel now contributes 1.5 atmospheres after it's opened and mixed. The other one expands into that same volume and it contributes 0.75 atmospheres. The total pressure is the sum of those two, 2.25 atmospheres, and that is between 2 and 3. Okay, so we used Dalton's law of partial pressures and Boyle's law to solve this problem. Okay, I didn't go too far over. We're going to stop here and pick it up next Monday with the rest of this chapter 7. And in the interim, what I'll do is, actually I'll post the video for this one as part 1, or I'll designate it as section 7.1 to 7.8, so it'll be distinguishable from next Monday's class. Okay, I'm going to stop the share. Any questions, comments?